Hello everyone, so let's continue with our class. Let's see if this works properly. Last video was a little bit messy because of that. Okay, now let's jump to our app and we will continue with our class of heats of combustion. Very well. And we already have discussed what is a combustion, right? It's something that will be a fuel plus an oxidizer that is going to give you basically energy in the form of heat. And usually in the 20th century, it will also give you CO2. Okay, so that's the definition of a combustion. And today what we're going to discuss is a more typical combustion. So imagine that you have hydrogen, right? And hydrogen, usually the most common way in which we can find this element is in the form of water, right? And believe it or not, water comes actually from a combustion reaction. A combustion reaction because you will have to oxidize hydrogen with elemental oxygen, and I think that it's pretty obvious that at this moment, right? I think it's just fun that something that it's used to extinguish fire actually comes from a combustion, but anyway. And if you try to measure, right, the change of energy or heat that this reaction will release because it's negative, you will find out that actually it's a lot. It's going to be 285.8 kilojoules over mole. So it's a lot of energy, right? Just by burning hydrogen with oxygen, you will be releasing this amount of energy, and it is a lot, right? And it's not the only example, there are other ones. So sulfur, elemental sulfur, can also be burned with oxygen to give you SO2, okay? And this is going to release even more amount of energy. And it's going to be minus 296.8 kilojoules over mole. So it's more energy, right, than if you just burn hydrogen, but the problem is that this gas is very toxic. But anyway, now our world has been living in oil for the past 100 or so years, right? And this is because when we burn oil, we can release a huge ton of energy. So imagine that you have C8H18, which is another compound that you can get from petrol, and you want to burn these with oxygen. Well, the result is going to be the ideal combustion only will release CO2 plus H2O. Now, as you can see, this reaction is not balanced, so I'm going to balance it for you. You're going to require 25 half of oxygens for every mole of C8H18 to release 8 moles of CO2 and 1 mole of water plus heat, energy. And the heat that this reaction is going to release, right, is going to be minus 5,461 kilojoules over mole. So you can see it's even a lot more of energy, right? And there are other compounds that can release also huge amounts of energy. But every single one of them is going to obey Dalton's rule, okay? So if you have C8H18, and this is going to release minus 5,461 kilojoules, right, for every mole, right? That means that if I multiply this by 2, then I also have to multiply this by 2. Sorry, no, wait a second. If I multiply this by 2, now that is correct, I also need to multiply this by 2. Very well, so I would get for 2 moles of C8H18 a release of energy that is going to be minus 10.922 kilojoules, okay, and so on and so on. So for example, if I have 0.3545 moles of C8H18, I will be releasing, that's why the minus, 1,935.92 kilojoules, okay? And this is the fuel that I'm burning, and this is the heat that burning that fuel is releasing. So let's go and jump into a problem to see what we can do with that. So there's a gas that it's called acetylene, right? And it has the formula C2H2. If this is not the correct way to spell it, please let me know. I just don't remember how to spell it right now. And you can burn it, right? And if you're performing a combustion, we know that it's going to release CO2 plus H2O. The problem is that this reaction is not balanced, so let's go and balance it. And you will need 5/2 of oxygen to burn 1 mole of C2H2, release 2 moles of CO2 and 1 mole of H2O. And the amount of energy that you will release for burning 1 mole is going to be a lot, minus 1,301.1 kilojoules over mole. Okay, so every time that you burn 1 mole of this gas, you're releasing this amount of energy, which is a lot. So let's go and jump into a practical problem. And let's say how much the temperature of, going to change color, 0.2698 grams of aluminum, right, will rise if I heat with 1.75 grams of acetylene, right? If I burn it and I have two considerations. Number one, the initial temperature of aluminum is going to be, let's say, for example, 25 Celsius, okay? And this is the most important one. The whole heat transfers to aluminum. That means that for every single mole that I burn, it's going to be transferred to what? To the aluminum. Very well, and that's a very important consideration, and you will see the consequences of doing that. So anyway, let's go to the books and get some info that we might use. So for example, the aluminum has an atomic weight of 26.98 grams over mole. It's pretty obvious that we're going to use this information, and I know also that C2H2, right, is going to release, it has a molecular weight of 26 grams over mole. It's a coincidence that numbers are similar. Believe me, I was not willing for this when I was performing this exercise. Anyway, so let's go and say, right, how much energy actually I am going to release with 1.75 grams of C2H2. And for that, it's pretty simple. We're going to summon Miss Jose. And I know that 26 grams, right, of what? Of C2H2 are going to release minus 1,301, this is a 0, 201 kilojoules. Very well. If I have 1.75 grams of what? Of C2H2, right, then how much I am going to get? Well, pretty simple. You send an arrow, you multiply, you then divide, and what you get is minus 87.56 kilojoules, basically. So what we are doing is that I have what? 1.75 grams of C2H2. And then what I am doing is that I am burning, okay, this amount of energy. Knowing this number, and after I perform the burning of the gas, I know that I'm going to have minus 87.56 kilojoules of energy, right, released from that combustion. So that's important. That's important. Very well. So let's jump to the next step. So the heat of combustion, right, that I got from this reaction was minus 87.56 kilojoules. Very well. Now I need, with this number, right, to figure out how much the temperature of aluminum is going to change. And I have to perform now a new analysis for this. And we're going to use the same model of boxes, right, that I use for thermal equilibrium, but this is not thermal equilibrium, this is energy transfer. And that is going to be absolutely different. We will see the consequences of that. So I have what? Aluminium, right? And I have what? C2H2. But in this case, I don't care that the temperature of aluminium gets the same as the temperature of whom? Of acetylene. No, that model is not going to work, okay? For a very simple reason. What we're doing now is that we are burning. We are burning C2H2. So we are transforming C2H2 actually into what? Into heat. And I'm going to say that this heat is going to be fully transferred to the aluminium. So what I'm doing is that minus 87.56 kilojoules are going to be transferred to the aluminium, and then I can figure out what is going to be the change of energy. So if that is true, let's go to another page, right? I need to set up that the change of heat of the combustion is going to be the same as the heat of combustion. We already know that. And I have to relate this somehow to what? To the change of temperatures, right? For the aluminium. And this is very important, okay? Now we have to work with the definition that the change of temperature is going to be TF minus T initial. Sorry, I made a mistake here. Minus T initial, okay? It's not like in the thermal equilibrium. In thermal equilibrium, we can use the absolute value of the change of temperatures, right? But this is only for what? For thermal equilibrium. And we can use the absolute value because the temperature, right, the energy is going to move both ways. In this case, no. In this case, what we will have, what we will have is that in our model, right, the heat is moving only in one direction. In the thermal equilibrium, right, the heat is moving in both directions. So that's why you can use what? Only the absolute value of the change of temperature. Here, it will not work because it's only moving from one side to another. So be careful with that. You always need to use, in this case, the difference between the final temperature minus the initial temperature. And many books will not tell you that. You have to do, or you have to figure out that assumption by yourselves. That's why I'm helping you. Very well. So now that I have this proposal, now I need a way to solve it, right? So I know that the heat of combustion is going to be the same as what? As the change of temperature of aluminium. But since I transformed this into an equation, right, I need to use a model that I know. And what about if I use the model of a specific heat capacity and make a dimensional analysis to see if this is going to help me? And for me, it makes total sense, right? Let's rearrange this into something that you might notice familiar, right? And if I say that I am going to measure the amount of heat that was transferred to the aluminium by knowing what? The change of temperatures also of aluminium, then I can conclude that this equation is going to help me to figure out what? The final temperature. So let's go jump numbers, okay, and see what is going to happen. So I was telling you that heat was transferred to aluminum, right? And this is very important to solve the exercise. Very well. So since it was given, that means that the aluminum is receiving energy. How much energy is receiving the aluminum? 87.56 kilojoules. This heat, okay? Now let's go jump to the equation. And I'm going to say, well, first of all, let's deal with the change of temperature. And the change of temperature is going to be the final temperature minus, I don't remember, 25. No, let's say that it's 30 Celsius. I know it's 25, but I resolved the problem for 30 Celsius. Okay, times 0.2698 grams times the specific heat capacity of aluminum, which is 0.9 joules over grams and Celsius. Very well. So let's erase this part. Excellent. And it's pretty simple, right? The only thing that we need to do now is to clear this incognita, right, from our equation. And it's going to be plus 87.56 kilojoules, right, over 0.9 joules over grams over Celsius times 0.2698 grams plus 30 Celsius, the same as final temperature. So let's just go back and say that I'm going to calculate it for 30 Celsius. Sorry, my mistake. Very well. Excellent. So when you perform all of these numbers, right, you will see that the final temperature is going to be something quite absurd. It's going to be 360,536 Celsius plus 30 Celsius, right? So the final temperature is going to be above 360,000 Celsius, right? Which is a lot. That means that the aluminum is being transformed into what? From a solid to literally plasma, right? If I apply all the heat from burning, right, the C2H2. And of course, if we perform this experiment in a welding exercise with any blacksmith that you know, right, you're going to see that is not the case. So is the model wrong? No, absolutely not. It's just a special consideration. So imagine that you have your aluminum, okay, and that you're going to use C2H2 in the form of a torch to perform what? A welding. Okay, so imagine that you have what? Here, your piece of aluminum. Imagine that it's cracked, it's broken, right? And you need to repair it. So you're going to get your torch with acetylene, C2H2, and you're going to burn it. This is a flame. I know that I draw horrible. Doesn't matter. So according to this equation, right, if we burn 1.70, what? 75 grams, right, of this heat, I am going to transfer the amount of energy. Give me a second. of minus 87.56 kilojoules. Very well. So this is the amount of energy that the burning is what? Releasing. Now I am going to transfer that energy to the aluminum. How much? Plus 87.56 kilojoules. But the problem is that the torch, right, is not releasing the energy only towards what? The piece of aluminum. A lot of the heat is escaping, right? So actually we are not adding exactly 87.56 kilojoules. We're only adding what? A fraction of that energy, so we can fix our aluminum piece. Most of the energy actually is what? Escaping. So it's not that the model is wrong. The only thing is that the model is ideal, right? If I use Q the same as Cm change of T, and I assume that I am going to transfer the whole amount of heat to what? To the aluminum, right? It's only the ideal model. But it works quite well for other problems that you will have to solve in your professional life. So I hope that this example has been enlightened. Sorry, I've been having a lot of problems creating content. I appreciate your patience and see you next video. Goodbye.